All right, welcome everyone. Great to see you here. Again, my apologies about the Zoom link. I have fixed all the other Zoom links, so that will never happen again. So thanks for being here. I apologize for that. We are here for our monthly 30-minute power session. Today, we're going to really look at, I'm going to make a claim today, actually. And the claim that we are making as ASTA is that if we leverage science instruction as intended by the research behind our standards, we can actually enhance ELA outcomes. So that's the claim I'm putting out there today, and I hope you find evidence to support my claim as we work through this session together. So as always, we'd love to see who's with us. Say hello in the chat. Tell us, what school, what district, where are you coming from, just so we can all say hello really fast. And we got more folks coming, so that's great. Good morning. Welcome. Welcome, welcome. All right, Paradise Valley, good to see you. Okay, we got folks all over. Folks from St. Louis, Missouri, great to have you. Hey, Peoria, Prescott, Littleton, wonderful. Deer Valley, hello. Arizona Department of Ed is here, awesome. Great. Oh, Katie's here from Michigan, hello. Good to see you. Carrie's here from Phoenix, good to see you. All right. Great. So we've got folks from all over coming in. And so good morning and welcome. We're going to get moving. Sarah Torres and I developed this session together, but Sarah could not be here today, so I will be your pilot. And with me is Judith Lazoya, our communications director. She's going to help me with links and questions in the chat. So a reminder that you're here today for ELA, but next month, we are going to talk about learning targets. I know folks have been asking us a lot of questions of how do you develop learning targets for three-dimensional science instruction. So we're going to work with a district, a friend of mine that works at a district, a colleague, and we're going to put together this session on what do three-dimensional learning targets look like. And so hopefully you come on back in November. But for today, here is what we are up to. So I invite you to read these goals for our short experience today. All right. So our mission today is really to look at how science and literacy really have this synergistic relationship. And to get us started, first of all, does everybody have the link to the resource collection? As always, I build you one of these resource collections. So make sure you've got that open. And it looks like everybody does. Okay, so as we go, I will be calling out numbers of resources that we're going to open. Later on, after the event, I will link the slides and the recording right here. So all you need is this resource collection and you can have everything. Okay, hope that works for everyone. Everybody good? Looks like we're all in there. So in the chat, to kick us off, I want you to dig into your own mind. Think about your mental model of science instruction. So when you think of what goes on in a science classroom, what comes to mind? In the chat, jot down some ideas. What is your mental model of science instruction? So I invite you to come into the chat, talk about what is immediately popping up in your head right now. So what is your mental model? All right, we got facilitator. We've got reading informational text, hypotheses, labs, phenomenon, notice, wonder, communication, reading, writing, speaking, listening, and engage with phenomenon. Students are talking, getting messy, labs, collaboration, discussion, investigating. Wonderful. Exploring, experimenting, talking, drawing, discussions. All right, and all other ideas are welcome. And so we all come with our mental models of what we think science instruction can look like, especially if we're an administrator. So I want to help us think through this. In mental models, kids also have those mental models, right? Like we often view scientists as somebody who looks like this, right? That crazy kind of scientist in the lab coat. Just like kids have those mental models of science instruction, or sorry, what scientists look like, we also experience these mental models when we're out in the field working with folks
If you need
on
to,
uh, things that look like this. So oftentimes folks think of science as like, let's label diagrams, like the classic plant cell, or let's talk about the different parts and label parts of DNA. Or we're going to give kids like a reading and then ask some comprehension questions. And then science is all about these science terms. And so I'm happy that your mental models don't really fit what I was expecting you to say, which is wonderful. But I know from experience working with over 60 districts across the state is that we still have traditional mental models of science being all about memorizing facts, labeling diagrams, recall type of instruction, giving kids something to read and then answer comprehension questions about. That still is considered some typical science instruction when we go out in the field. And so I'm so happy that your mental models go way beyond that. So that makes me very excited about what we're going to get into. So we know that science is much more than just memorizing those facts, and it can manifest in a variety of ways in different professions and ways of knowing out there. It could be folks working on diagrams and building structures, or out in nature journaling, or reading heavy research and trying to figure things out, or working together collaboratively to make sense of the world around us. And so, when we talk about what goes into science instruction from a literacy or an ELA standpoint, we really need to broaden our scope of what students are doing in the science classroom, which you all said in the chat. So if we think three-dimensional science instruction and have these ELA components, right? Reading, writing, speaking, listening, vocabulary. Where do these things show up in science? Well, first and foremost, we always are reading to gather information. It's actually one of our science and engineering practices of obtaining, evaluating, and communicating information. So we are always leveraging text to support our thinking and help us explain phenomena. We also help students with claims, evidence, reasoning type of writing. We also have writing a ton inside of our notebooks for making thinking visible in a variety of ways. Notice wonder, drawing models, explaining our models, speaking and listening. A lot of our classrooms out in Arizona have these amazing accountable talk stems or productive talk stems where we teach kids how to talk, integrate ideas, reason with each other, and push back gently on each other in the spirit of co-collaboration. We also use a variety of talk formats. We give kids alone zone time, time to think on their own and process metacognitively. We move them through partner talk, small group work, and teacher led whole group discussions, which sometimes are called scientist circles. Additionally, the mental model that we're trying to steer away from is that science is all about memorizing facts, when in fact, we do leverage science terms in a way where students will earn those vocabulary words over time, not memorize them. So we leverage word walls where we co-construct a definition after we've had an experience with that word. We then, even in younger grades, this is a word wall from a second grade unit we wrote, we help the students match those words to the experience, even in the lower grade. We also develop what are called gotta have it checklists, which have key ideas, key terms the students need to leverage and apply to their models in writing, drawing, speaking, and listening. So if we're teaching three-dimensional science the way it was intended, we are doing reading, writing, speaking, listening, and vocabulary all at once. So why does this matter and where are we going on this journey now? Because science is a very powerful context for literacy, but often science gets pushed to the side. Students in science, the way it was designed through the NRC framework, which is what our standards were from, is all about students reading, writing, speaking, listening, with an intentional purpose about figuring out the world around them through phenomenon or engineering problems. Additionally, integrating literacy components in science is what we automatically do naturally. It's not an afterthought for us because our goal is to get the kids to communicate. And that is about building deep conceptual understanding and comprehension. And so, as we work together, I want you to keep this idea in your mind. How might improving science instruction in your school, in your district, in your system simultaneously boost ELA outcomes in your schools? So to help us think about this, I want you to watch a classroom in action and look for literacy components. I grabbed one of my most favorite videos that I've been using for years to hone in this idea. This comes from Ambitious Science Teaching, which we've done community of practices around. We've done book studies. This video is going to help us really identify literacy components. So here's what we're going to do. As you watch the video, I want you all to pay attention to how science instruction includes or could include, like when do you see those moments for those ELA and literacy elements? As you watch the video is a good 5 minutes or so. Jot down ideas of how the teacher builds in those strategic intentional planning moves for students to read, write, speak, listen, and keep an eye out for how they're using very technical vocabulary. Be ready to share 2 examples of how literacy and science are working together. Does everybody feel all right about what we're going to do? Looks like people are pretty ready. So remember, jot down where you are seeing literacy components, speaking, writing, listening, and vocabulary. Here we go. Actually, it's 6 minutes.
This third grade sound energy example will show how students created and refined models over time which supported their ability to write scientific explanations. We used a focal phenomenon in order to anchor the unit around an underlying big question that students could pick apart and wrestle with throughout the unit. The big question for this unit was, why can a singer shatter a glass with his voice? Students saw 2 video clips about this phenomenon, then talked to each other right after watching, already curious about what was happening.
Yeah, then it gets so wiggly.
Yeah, the bottom is wiggly.
Oh, look at that!
Okay, so I'd like you to pair. Are you guys next to your pair?
My buddy's on here.
Oh, if you don't have a buddy, can you join another buddy, and buddy up, and I want you to talk to your buddy about what you see happening, and take turns, right?
I think it's vibrating and like it's shaking because the bottom. I think he's kind of going toward the bottom, and it's like kind of circling around the glass, which is making it not fall over, and like shaking it. And then it just gets so shaky, and then it just breaks. Yeah. We were wondering why it's going back and forth. What does that mean? How would that change? It's supposed to be this. It's not break because when it's storage, you're putting water in it, not for breaking the voice. So it's shaking so much and it's so hard that it kind of just shatters.
Using a model scaffold provided a structured space for students to diagram and outline their initial ideas. They had time to talk with others about their initial ideas and add or change their models. Here are some examples of students' initial ideas about the big question, why can a singer shatter the glass? During the unit, students made sense of various activities and demonstrations as they layered on knowledge about how our bodies produce sound, how we hear sound, the force and energy of vibrations, how sound travels through different media, and a bit about resonance. Students revisited their initial ideas a little over halfway through the unit. We also talked about diagram norms and focusing on only including details, labels, arrows, and explanations that were about our science ideas. From this model, we could see gaps in student understanding and made instructional decisions on the activities in coming lessons. Students use these conversations to further develop their model and explanation.
Agree with you because I think the sound waves are like invisible waves that are made out of sound, and that like sound waves is making sound waves, and this is vibration. But I'm still making a noise, and it's still traveling. So why is it not the same as sound waves? But what if sound waves has something different in it? I know, but sound is still traveling.
Finally, students worked in small groups to make a consensus model that would explain how the singer was able to shatter the glass using evidence to support their ideas. Students had resources to help them in this process by using their initial model and midpoint model, as well as access the readings and diagrams we have used in class.
And what we figured out is that I put my ear to a table, and then I just gently knocked on it, and then I pulled my ear back and I knocked the same force, and it was actually quieter. So we figured out that sound travels through things.
But it can travel then the farther it goes. Like, so we were in the hallway, and so I talked to Emma like way up close, like really close, only like
that.
like that, like hello. And then we went really far away, and then
I literally went like to the second floor.
Oh, did a little experimenting.
and then but I couldn't hear her. So we figured out that if the sound wave travels like really far, it kind of like builds off some of the sound, and so then it's only small, like it expands all over.
So, and it only comes with a certain amount of force.
Mm-hmm.
After presenting their small group models to the class, students gave each group feedback about their ideas. This feedback would help groups clarify their diagrams as well as help focus their writing. To help scaffold their writing, students had pink sentence starters that were about ideas and green sentence starters that referenced activities to help students bridge what they learned in the activity and use it as evidence for their ideas.
One thing, the singer doesn't have enough force to break it, so it takes longer to break.
Wait,
We need
force
to write
to break.
evidence. We need evidence. How about you don't need to use the green evidence thing. How about you just write some evidence?
What I wrote about is the singer can make sound because the diaphragm squeezes the lungs, which pushes air through the vocal cords. The vocal cords vibrate the air. That makes up sound waves.
I've got one question.
Yeah.
You forgot the diaphragm. Diaphragm, right?
The diaphragm.
Yeah.
So I have to draw a muscle.
Well, technically the diaphragm helps the air come out, right?
Yeah, I know. It explains it. The diaphragm squeezes the lungs, which pushes the air through the vocal cords.
Oh, I wasn't listening correctly because I didn't hear the
You
right
need
guy.
hearing aids.
Throughout the unit, taking time for students to refine their models of this science phenomenon and communicate their ideas with others provided them with the resources needed in order to craft a full scientific explanation about a sound energy phenomenon.
All right. So that is the end of the classroom video. So in the chat, just take a moment and share what are two strong examples of either reading, writing, listening, speaking, or using precise vocabulary. So I'll give us about a minute of time to get everyone's responses in the chat. So come on in. Where did you see some examples of literacy and science working together? Okay, thanks, Laura. We got writing their claim, supporting evidence, reasoning, group discussion, collaboration. Yep. Scaffolded writing. Yep. Pink and green sentence starters, sentence frames, right? Initial and midpoint models. Yeah. And then they had consensus models, right? Writing and vocabulary. Different models. They were talking, combining ideas in those models. Yes. Precise use of vocabulary evolved. Love it. Thank you for sharing. Multiple sources, right? Investigations, reading, talking with others. Yes. Wonderful. Discovery, then research, final explanations. They use the vocabulary diaphragm and vocal cords and sound waves, right? Yes. Feedback and clarification. So many examples. They use terms as they explain their thinking. Absolutely amazing. All right. Thanks for sharing. I'm just going to gently push us forward. So what you saw at the very end, or sorry, throughout there, you saw, you didn't get to see them reading, but there was reading. They read about sound waves and then they applied that stuff to make sense of the phenomenon. They also had a lot of data from their investigations, and then they were writing and arguing. You heard them, right? Writing with the sentence frames, talking about their claims and evidence. They were completely speaking and listening the entire time, using each other's ideas to refine their own thinking and really work together to co-construct knowledge, the way scientists do in the real world. And you all said they had vocabulary as well, right? Really earning those terms over time, not memorizing those facts, but using them in service of explaining the phenomenon. So, one thing I wanted to call out is at the end of the video, you saw these two things called out. These are the science and engineering practices. We have specific practices that are very ELA heavy. So I want to go down this rabbit hole a little tiny bit. And reminder that our standards are built with 3 dimensions inside of them. The practices are those verbs through which the students perform and actively do science, right? Arguing from evidence, constructing explanations, obtaining information. So reading, writing, speaking, listening are all embedded in this dimension. Vocabulary lives in the core ideas and cross-cutting concepts, using patterns, talking about cause and effect relationships. And so when students are really doing all 3 of these dimensions, they're practicing literacy because they are purposefully communicating the entire time. So take a look at our science practices. We have 8 of them. You saw obtaining, evaluating, and communicating. That is our very, very ELA heavy practice. You saw engaging in argument from evidence, claims, evidence, reasoning. You saw constructing explanations and, all that stuff. And a reminder that our standards start with one of these verbs through which the students are going to perform. In every standard, this is the blue part that begins every single one. Now, why am I asking you to think about this? Because I want you to think about the practices, how students perform science, and how naturally they are tied to ELA. So we're going to open our first resource, go to number 3, and clearly let's see. So take a look at this, number 3. And just take a quick 30 seconds and just these S's here stand for our science and engineering practices. Where do they have commonalities with ELA? So look for the overlaps of S's and E's. And I'll give you about 30 seconds to kind of just look high level because we're going to go deeper in just a second. And so hopefully you're noticing some overlapping happening here, right? We have some things in common with ELA. So let's take it now a step further. Now that we've looked at that, I want you to take another look at a fabulous resource that aligns our science and engineering practices to literacy expectations. And I borrowed this table from this incredible National Research Council document called Literacy for Science. So we're going to open number 4A, and I want you to read, these are our science and engineering practices and how they align to literacy expectations. And then in the chat, I would just love to know, wow, what is really one of these that what are these practices that naturally align with what you're seeing in your teachers' classrooms? Like, what science practice aligns with the ELA? So number 4A is this table. I'll be quiet and we're just going to read over the table. And then just let me know, like, what things are you already seeing connections with in the classroom? So I'll give us about 1 minute to read that. I don't think it'll take 2. Ooh, okay, so we see asking questions, communicating, yep, developing evidence, arguments, yep. Other ideas? Meaning, yeah, communicate. We are the communicators, right? Science is all about communicating. Yes, arguing, thinking about which explanation is the best one out there based on the evidence. Yes. Present findings. Yes. Perfect. So you kind of see where I'm going with this. And so I know we're almost at time. So what I decided to do is give you resources to further your knowledge that you can use on your own. So thank you to those who participated in the chat. I know these are like the super shortest meetings ever. I was hoping we were going to have time to read this, but that's okay. Let's get you introduced to one of my favorite resources. What I'd like to show you is number 5 in the resource collection. So let's just go grab it. This comes from the NGSS, right? The Next Generation Science Standards. Yes, I know Arizona is not an NGSS state, but our standards were built from the exact same document, the NRC framework. And so this is an appendix that goes with the NGSS. And what it lays out for everybody is how our science and engineering practices align to literacy. So come on down to at least page 2. You'll see the science and engineering practice, which we have 8 of them. They are in our standards, not on the side like math has them. And then how it supports connections to some of those Common Core state standards. Again, I know Arizona's not Common Core, but you all know what I'm talking about. And then really how this stuff is connected. So how are those Common Core pieces for reading and ELA written and combined with our science and engineering practices. So if you're looking for specific evidence on how science can be integrated with reading, writing, speaking, listening, it is all in this document. So I just wanted to bring this resource out and make sure that everybody know it's on your resource collection and you have it. So finally, our key takeaways on our way out. Realizing science automatically integrates these ELA pieces. It's not an afterthought for us. It is naturally occurring every single moment of our classroom time. Phenomena-based and problem-based instruction really can help boost those ELA outcomes with those intentional strategic purpose and planning. And literacy growth does happen through science, not apart from it. So if we want to boost ELA, let's teach more high-quality science. And a reminder that this is how science is done in the real world. It's all about reading, writing, thinking, and communicating just like scientists. And my final resource for you, I gave you this amazing article called Science Plus ELA, A Natural Fit, which is number 6 in your resource collection. So I just pulled a quote from there to get you excited because it talks about how writing can be boosted through science. And so I know we're at time. These always go so fast. But a reminder, next month is about learning targets, and Judith is going to put a link in the chat. I'm glad you love the resource. I have to be very choosy in 30 minutes, so thank you for that. If there are other topics you would like us to cover, that's what that feedback form is for. So if you're like, we're really struggling with X, could you build us something to help support that? Or would you like to do a session on blank? That's what the feedback form is for. Again, thank you for your time, and I will see you all next time. Oh, I'm glad. 30 minutes is so hard, so thank you for that. I just want to get some resources in your toolkit. All right, good to see you all. Thank you for coming. Stopping the recording.